As a participant in the Federated Marine SDI Pilot Phase 3, Ecere demonstrated its Gnosis Cartographer client interacting with the discrete global grid system server provided by the University of Calgary. As users pan and zoom in the 3D view, the client requests the result of a coastal erosion susceptibility workflow from the server, triggering calculation on the fly for the area and resolution of interest. A discrete global grid system, DGGS, tessellates the Earth at multiple resolutions, with each resulting zone being assigned a unique identifier. Both vector and raster datasets can be quantized to these zones, allowing to perform efficient data integration and analytics. The University of Calgary server implements an icosahedral Snyder equal area aperture 3 hexagonal ICEA 3H DGGS. The shape of most zones in this grid is a hexagon, with the exception of 12 pentagons, as hexagons alone cannot fully tessellate the surface of a sphere. The ICEA 3H grid is hierarchical, with each hexagon generating a centroid child as well as 6 vertex children for the next level. These vertex children are shared with 2 other parent hexagons. Aperture 3 refers to the fact that from one level to the next, there are 3 times more hexagons. The use of the ICEA projection, described by John Parr Snyder in his 1992 paper An Equal Area Map Projection for Polyhedral Globes, ensures that all zones at a given hierarchy level cover the same area. The 12 pentagonal zones are an exception, each occupying 5/6 the area of a hexagonal zone. One remaining difficulty for widespread use of these equal area DGGS is support for the ICEA projection in foundational geospatial tools such as the Proj library. At the moment, Proj only supports the forward projection, but not the inverse. However, an MIT-licensed implementation of the ICEA projection is available from the GeoGrid open source project. To facilitate requesting and integrating data from the DGGS server into the client, a dual DGGS of the ICEA 3H based on rhombuses was used, sidestepping the complexity of hexagons and pentagons. This DGGS, named ICEA 9R in this project, has rhombic zones whose vertices are centered within the hexagon and pentagon zones of the ICEA 3H even hierarchy levels. Therefore, an area value in ICEA 3H becomes a point value in ICEA 9R. From one level to the next, one rhombus zone is split into 9. Each of the 10 root rhombuses of the ICEA 9R level 0 corresponds to 2 triangles of the ICEA projection joined at their base. Those 20 triangles have their vertices centered within the 12 pentagonal zones from ICEA 3H level 0. Rhombic grids of values can easily be encoded in traditional imagery formats such as PNG and GeoTIFF by mapping the skewed rhombus grid to a rectilinear grid. They can also easily be cached in GPU textures. Compared to hexagons and pentagons, rhombus zones are also much simpler to index. The native DGGS of Ecere's Gnosis visualization software is based on the Gnosis Global Grid tile matrix set, which is defined in a flat carré coordinate reference system. The grid tends toward equal area by using a variable number of tiles along latitude bands, reducing the number of tiles toward the poles. Although the exact area of any zone is easily calculated, and the alignment with latitude and longitude grids greatly facilitates importing and exporting data, this DGGS does not qualify as equal area since the zone area still varies significantly. During this phase of the FMSDI pilot, participants realized that it was also possible to define a set of tile matrices based on the ICEA 9R DGGS. Tile matrices are the foundation of the recently approved OGC API tiles standard, as well as the older, widely supported OGC Web Map Tile Service, WMTS, and OGC GeoPackage. Registering an ICEA 9R 2D tile matrix set should greatly facilitate the access and usability of data organized according to an ICEA 9R or ICEA 3H DGGS. The first tile matrix is defined starting from the ICEA planar projection of the globe to an unfolded icosahedron. The orientation used is the standard Ecere orientation with a single icosahedron vertex falling on land. The 0,0 origin is assigned to the vertex west of Alaska. A 60 degrees clockwise rotation is applied, followed by a 30 degrees skew, which turns the rhombuses into rectangles. Finally, the rectangles are scaled, resulting in 10 valid square tiles out of the 30 potential tiles in this transformed 2D space. For an aperture 9 tile matrix set, each tile is split in 3x3 at the next level. Tiles of each tile matrix are indexed by row and column in the usual manner, starting with the top left tile as 0, 0. Based on a coordinate reference system, including the affine transformation used to define these tile matrices, an equal area Ecere 9R DGGS can be defined where all zone edges are aligned to the axes of the CRS, resulting in a very convenient DGGS which is equal area as well as axis aligned. Ecere implemented this tile matrix set and DGGS in its Gnosis map server with support to request zone data using either OGC API tiles or OGC API DGGS, as well as the ability to query where data is located through OGC API DGGS zone queries. In this Ecere 9R implementation, the zone IDs are defined based on the level, root rhombus, as well as a hexadecimal identifier combining the row and column within that rhombus. The datasets used in the coastal erosion workflow visualized here included the digital elevation model, the superficial geology of Alaska, a global land cover map from Landsat, and a map of the circumarctic permafrost. The digital elevation model values first go through slope and aspect processes in order to produce two distinct values, each independently contributing to the erosion susceptibility. This workflow can be defined using OGC API Processes Part 3, Workflows and Chaining, extending Part 1 core JSON execution requests. This allows clients to integrate multiple data sources and processes, providing algorithms and computing resources wherever they are located, and instantly visualize the results. Expressions written using CQL2, the OGC Common Query Language, can be used to map properties from the datasets to a numerical estimation of how much they could be contributing to erosion, and to specify final weights in order to output a single susceptibility percentage value. A key takeaway from this FMSDI pilot DGGS activity is that an equal area and axis-aligned DGGS, as well as a 2D tile matrix set based on rhombuses, can be defined to greatly simplify the access to data indexed with multiple icosahedral Snyder equal area DGGS, whether using OGC API DGGS or OGC API tiles. These data access mechanisms, together with the ability to define filters and derive fields expressions with CQL2, can be used to trigger the execution of processing workflows defined with OGC API Processes Part 3, enabling researchers to easily integrate the datasets and algorithms they need to address challenges such as coastal erosion.